Hi, welcome to Algebra 2, Topic 6, Exponential and Logarithmic Functions. In this lesson, in this topic, we'll be able to think about this big topic essential question: how do you use exponential and logarithmic functions to model situations and solve problems? We have 7 lessons total in this topic, starting with key features of exponential functions, exponential models, and then moving on to logarithms and log functions, properties of log, exponential and log equations together, geometric sequences and series in relation to the exponential and log functions. We do have a lot of topic vocabulary, mainly related to exponential and log functions. So this will be a good review for exponential properties and functions, as well as learning log functions and log equations to be more effective in solving problems related to exponential functions. So we are going to start with lesson 1, key features of exponential functions. In this lesson, we'll be able to recognize the key features of exponential functions. The lesson vocabulary would involve decay factor, exponential decay function, exponential growth function, and growth factor. So let's start with explore and reason. Margaret investigates 3 functions: y equals 3x, y equals x cubed, and y equals 3 to the x power. She is interested in the differences and ratios between consecutive y values. Here is the table she started for y equals 3x. So Margaret made a table for the first function where she made a table of x and y values, and then she figured out the difference between the y values and the ratio between y values. So part A, create tables like Margaret's for all 3 functions and fill in more rows. So just like this, we're going to make a table like Margaret's for the next 2 functions. Let's move on to y equals the next function, y equals x cubed. So first of all, you want to find the values for x and y. We can add some negatives here. If it's -1, you'd have -1. And then if x is 0, y would be 0. If x is 1, y would be 1. If x is 2, finally, y would be 8. If x is 3, y would be 27, and so on. So the differences between y values would be 0 minus 1. So 0 minus -1 would be +1. And then 1 minus 0 is 1. 8 minus 1 is 7. And then 27 minus 8 is 19. And then the ratio between the y values would be 0 divided by -1, 0. And then 1 divided by 0, undefined. And then 8 divided by 1 is 8. 27 divided by 8 is just 27 over 8. Okay, and then let's... So this is one more table. And then let's draw another table. Let's see, over here. So y equals 3 to the power of x. Let's start with the x and y values. We can start with -2 now. When x is -2, y is 1 over 9. When x is -1, y is 1 over 3. When x is 0, y is 1. When x is 1, y is 3, 2, 9, 3, 27, and so on, 481. And then differences of the y values would be 1 over 3 minus 1 over 9 would be 2 over 9. And then 1 minus 1 over 3, 2 over 3. 3 minus 1, 2. 9 minus 3, 6. And then 27 minus 9, 18, and so on. And then the ratios would be 3. 1 over 3 divided by 1 over 9 would be 3. 1 divided by 1 over 3 would also be 3. 3 divided by 1, 3, 3, 3. Okay, so you notice something, right? Part B, which functions have a constant difference between consecutive y values? And what about constant ratio? So, difference between the y values would be the same for y equals 3x. And then for x cube function, it's all different. But then 3 to the x power would have the same ratios between the y values, right? Yeah, so what's happening here? First, let's write our observations. So for consecutive y values in the tables for each function, y equals 3x always has a common difference of 3, and y equals 3 to the power of x always has a common ratio of 3. Okay, so part C, which of these 3 functions will have y values that increase the fastest as x increases? Why? So if you look at the differences in ratio, just by looking at it, your difference just make sure that you're going to add the y value. Your y values would increase by that much factor, right? But the ratio tell you it's the y values are going to increase by multiplying that factor. So obviously, just by comparing y equals 3x and y equals 3 to the power of x, you know that y equals 3 to the power of x would increase much more faster, right? Yeah, so comparing these information, we can tell that the last equation will increase the fastest because the difference between consecutive y values is greater for y equals 3 to the power of x than for the other 2 functions. So it is increasing this is decreasing. So y equals 3x. No, 3 to the power of x. So it is increasing the fastest. Also, the other 2 functions have decreasing ratios, so they are increasing at a slower rate. Yeah. So just by looking at the ratios, you can tell if it's increasing steadily or if it's increasing at a slower rate or if it's increasing or if it's not increasing. All right, so this lesson is all about key features of exponential functions. And let's think about how the graphs and equations reveal key features of exponential growth and decay functions. So let's start with example 1. Identify key features of exponential functions. What are the key features of each function? Include domain, range, intercepts, asymptotes, and end behavior. So an exponential function is a function of the form y equals a times b to the power of x, where a and b are constants, with a not equal to 0 and b is greater than 0, and b is not equal to 1. What happens if b is equal to 1? Then it is not an exponential function. It's just going to be a linear function, right? And if b is greater than 0, then that means b is positive. If b is less than 0, then you have a negative function that's not going to look like this. And if a is 0, then everything becomes 0. So these are the restrictions we have. F of x is equal to 2x is a basic function, basic exponential function. That's a really good example to start with. So graphing this, your a is obviously 1, b base is 2, and then as x increases, your power of 2 increases, right? So then your 2 will be multiplied that many times, and so it increases exponentially. And then if it's a negative exponent, your base becomes rational, right? So then you have fractions, and you have an asymptote at y equals 0. So domain is all real numbers. You can plug in any numbers, but that doesn't mean your range would become negative. So because you have an asymptote at y equals 0, the x-axis. So your range is everything greater than 0, and it's not equal to 0 because it will never be equal to 0. Your end behavior, as x decreases, y approaches 0. As x increases, y approaches positive infinity. And the y-intercept is 1. So a lot of exponential function will have a y-intercept of 1, especially the parent functions of each base. So for exponential functions, your bases are constant, right? So your parent function is just the base with that number. Yeah, so when we're talking about transformation later, we're going to talk about the same base. So you can't use a transformation when the base is different for exponential functions. That's one thing you need to remember. Let's look at part B in example 1. When you graph a b to the power of x, where b is a rational number, then you'll see that the graph is decreasing because every time you're multiplying by that fraction. And if you multiply by a fraction less than 1, then you know your number is going to get smaller and smaller every time. So this is an example of a decrease, a decay factor, a decay function. So your domain is still all real numbers. Your asymptote is still the x-axis. Your range is still all positive numbers greater than 0. So domain range doesn't change. Asymptote doesn't change. When would an asymptote change? When your graph moves up or down. So think about translation, vertical translation. If the whole graph moves up, your asymptote also has to move up. So that's when your asymptote will change. But if you multiply numbers and your bases, it doesn't affect your asymptote. That's one thing. That's another thing to be mindful, and we're going to look at that in the next example. Let's continue looking at the key features. The end behavior, as x decreases, y is going up to the infinity, positive infinity. As x increases, y is not going to negative infinity because it's not going to be negative, right? So it's approaching 0. So you need to make sure if it's approaching a constant number, then you need to indicate that in the end behavior, especially when you have an asymptote. That's when you'll have an end behavior approaching to a certain number. And the y-intercept is 5. And you'll notice that the initial value a would be the y-intercept because anything to the power of 0 would be 1. And so that a times your 1 when your x is 0 would be your y-intercept, right? So yeah, that would be the key features of exponential function. Let's look at try number 1. Graph f of x equals 4 times 0.5 to the power of x. What are the domain, range, intercepts, asymptote, and the end behavior for this function? So remember to figure out all domain, asymptote, range, end behavior, and y-intercept as key features. Pause the video, see if you can do it by yourself. Come back when you're ready for answers. Okay, are you ready? First, you need to graph it. How do you graph it? Well, you need to write table of values, right? So first, you can write table of values. When x is equal to, let's say, -3, y is going to be 4 times 1 over 2 to the power of -3, which is 4 times 2 to the third power, which is 4 times 8. So that's 32. Yeah, and in the same way, when x is -2, y is 16. When x is -1, y is 8. When x is 0, y is 4. 1, 2, 2, 1, 3, 0.5, 4, 0.25, and so on. Yeah, and so in the graph, you can graph the x and y intercepts like this, and then you can graph the big points, 1, 2, 3, that's -3. And let's say this is 32. Now you can graph a point here, and then half of that would be 16, right? So -2, 16, and then half of that would be 8. So -1, 8, and then 0, 2, 0, 4, and then 1, 2, 2, 1, and so on, so that it decreases by half. Okay, and then your asymptote is still at y equals 0, right? So let's describe our domain range and the key features. So domain would be all real numbers. And then range would be anything greater than 0. And your asymptote is the x-axis. Your y-intercept is when x is equal to 0 is at 4. And then x-intercept, none. And then end behavior as x approaches -infinity, as x decreases, y approaches positive infinity. And then as x increases to positive infinity, as x approaches positive infinity, y approaches 0 because there's an asymptote. Okay, so 1, 2, 3, 4. Domain, range, asymptote, x-axis, y-intercept, the end behavior, we defined it. Check your answers if you got it right. If not, go ahead and look at it again. Let's look at example 2. Moving on. Graph transformations of exponential functions. Graph each function. Describe the graph in terms of transformations of the parent function f of x equals 3 to the power of x. How do the asymptote and the intercept of the given function compare to the asymptote and intercept of the parent function? So let's look at the g of x here. The function g of x is -3x to the power of x. When the sign of a changes, the function is reflected across the x-axis. Yeah, and then, and we know that the transformation, the negative will be a reflection, right? So when a is negative, it's a vertical change, so it's reflected across the x-axis. And when you have k, you're going to move the graph vertically. And it's a translation. So your transformations of exponential function would be summarized into this form, where you have a times b to the power of x minus h plus k, and then your horizontal stretch and compression would be a over here with the x, but we're not going to worry about that right now, okay? So yeah, when a gives two types of transformation. When a is negative, then it's a reflection across the x-axis. And then when a is between 0 and 1, So if it's positive, then it's going to be compression, vertical compression. And then when A is greater than 1, greater than positive 1, then it's going to be vertical stretch. Okay, and then H is horizontal translation, and K is vertical translation by a factor of blank units, up or down, left or right, right? So left to right, up, down. Okay, so yeah, so using this summary, let's look at chart number 2. How do the asymptote and the intercept of the given function compare to the asymptote and intercept of the function f of x equals 5 to the power of x? So compare this to the compare g of x and h of x to the parent function 5 to the power of x. I already explained that the parent function for the exponential functions would have the same base, right? If it has different bases, then you can't compare it, okay? So it has to be the same base, and the base of that, the parent function would be the same base to the power of x. So pause the video, see if you can define the transformations. Come back when you're ready for answers. Okay, are you ready? Yeah, so for part A, your transformation is 3 units. Your h is -3, right? So your transformation is 3 units to the left by a factor of 3, right? 3 units to the left. Or a horizontal translation by a factor of 3, by a factor of -3. So either 3 units to the left or horizontal translation by a factor of -3 would accurately describe this transformation. And then, yeah, if you want to check, you can also check the points where f of x is equal to 5x. Your points here would be -2, 0.04, -1, 0.2, 0, 1, 1, 5, 2, 25, and so on. So you don't have to compare them, but in order to visualize, you can also draw a nice little graph where this is true. And then 0, 1, 1, 5, 2, 25, and like that. Yeah. So this is f of x. Your g of x is the same thing, but move 3 units to the left. And let's see the individual points. You have -2. When x is -2, you have +3, so 5 to the first power is 5. And then -1, 25, and 0, 125, 1, 625, -3, 1, -4, 0.2. Yeah, and so you'll see that that it moved to the left, where it's like really big number over here for the y-axis, but then your asymptote didn't change. So yeah, f of x is here, g of x is here, it moves 3 units to the left. So yeah, you can check by graphing visually, but this is horizontal translation, 3 units to the left. And then part B, h of x is equal to 5 to the power of -x. And so the only difference is the negative. And so if you have a here, then you have a horizontal compression or stretch or reflection. So in this case, it's the opposite of vertical, because for horizontal transformation, everything is opposite, right? And if you have changed it horizontally, if you reflect it, it's going to be over the y-axis if your x is going to change, right? So this is actually the reflection over the y-axis. And then how do the asymptote and intercept of the given function compare to the asymptote and intercept of the function, the parent function? So we haven't answered that question yet, right? So here we know that this is going to be a reflection over the y-axis, which is going to look like this. And if you check by points, it's truly going to look like this. It's not going to go over than the so it's going to look something like this. So that's f of x, this is h of x. Yeah, and so how do the asymptotes change? The asymptote, so for part A, the asymptote, let me type this. The asymptote is the x-axis for both functions. And then does the intercept change? Yeah, the intercept changes from 5 to 125, right? So the y-intercept in this case is translated from 5 to 125. And then part B, your asymptote is still the same. The intercept would be the same if you plug in x equals 0, negative 0 is just negative, right? So the intercept is also the same. So the asymptote and intercept are the same for both functions. Okay, so that was try number 2 and example 2. Let's move on to example 3.